So I think in the last lecture I gave the definition of what is work and what is work done by a force, and we realized that the work done is only defined when we define the force. So we need to mention for which force we want to calculate the work. So just saying that find the work done is meaningless unless you do not mention the name of the force. So perhaps we saw two different ways of doing it. The first way was you multiply the force and take the displacement of point of application along the force, and we wrote as F S cos. And the other way was you take the component of force along the displacement, and in either case the end result is same, which we preferably write as F dot S. And for this formula to be valid, the force must be constant. So we say the vector F is constant. So because I'm saying force is constant, it means direction and magnitude both are constant, because force is a vector quantity. When we say constant, both are constant. Now, for variable force, we cannot write the same expression, but we have something to write. So for variable force, now this is for constant force. So for variable force, what we can do? Because we cannot apply this formula, then what is left for us? So for variable force, we cannot define the work done for the large distance because it's varying. But even though a force is variable, so even though a force is variable, over a elementary displacement, we can treat force as a constant force. So by nature, force is variable. But if you only consider the elementary displacement, let's say going from x to x plus dx, then in that small displacement, we cannot say it's variable. So let's say if we draw some random path, 2D, let's say plane. Let's say you go from A to B on this random path, which is y, this is x. So now this is random path. Now what we can say that if I take a displacement only from here to here, and if I call it ds, or is elementary displacement, and force is indeed variable, so it is acting this way. And if I draw a tangent here, so we can also see the angle between the f and the ds vector with, let's call it theta. So f will have a component along the displacement which is f cos theta. And for this elementary displacement, we can say the work done, not work done, we say elementary work done by the f, elementary work done by the f, we can write as the component of force along the displacement, which you can say f cos theta into ds, or the other way you can also do, you can take ds cos theta into f. So now what we can define is called the elementary work done, f ds cos theta. And so the total work done will be the integration of dwf. So for variable force, we have to eventually do the integration part. So we cannot just write f s cos theta freely as we did for the constant force. So variable force, the only way to write is integration. Now force is said to be variable even if it is changing the direction also. So variable force need not to be some function. If it is just changing the direction, that's good enough. So now we'll explore this more in the later part of this chapter. But right now, these are two definitions that we need to stick to. And this is sufficient to actually derive all other from. So let's do some basic derivation. So imagine we have an inclined plane, a normal inclined plane, and the angle of inclination is let's call theta. We have a small block at the top of the plane having mass m, and the coefficient of friction, let's call it mu. And we are assuming that it's going down, and the length of the entire plane is this. So this is the length of the plane is s. So when the block will go from top to bottom, it will travel s a displacement. And if it starts from rest, so by the time it will reach bottom, it will have some velocity. Now the question is simple: what is the velocity? So we can indeed do this by the laws of motion by finding the acceleration and then using the formula v square equals to u square plus 2as. But let's do this in the manner of work energy theorem, what we call later on. So first of all, we need to draw the FBD. So if we draw the FBD of the block, you can see clearly the forces which acts generally are the normal reaction. Now gravity will act vertically downward, mg, and because it's a rough surface, so it will also experience friction force backward. Now we have three forces, and we are supposed to find the total work done or the net work.
Or we have
So
to resolve mg also.
it's up to you. If you want to resolve mg along the s, you're free to do, or if you want to resolve s along the mg, that's also equally okay. So we have this freedom. Okay, we have this freedom to resolve either force along displacement or displacement along force if the forces are constant. So work done by total means sum of work done by each individual force, and the good thing is that we can calculate each value separately. So let's focus one by one. What is the work done by normal action? Tell me.
0.
Zero. So we have discussed in the last lecture that unless there is no displacement along the force, there is no work done. So definitely this answer is zero. So what is the work done by frictional forces? So whenever the force is opposing the motion, work is going to be negative, or you can think this way that the angle between the force vector and the displacement vector is 180 degree or pi. So F dot S will give you minus Fs. So what is the work done by kinetic friction?
So minus mg sine theta.
No, I'm asking the work done by Fk. How Fk is acting?
Opposite to the motion.
So what is the definition of work? Force into displacement.
Force into displacement.
So are you doing the same? Why? So just use the definition, no? Why you are applying your own brain? So what is the work done by kinetic
So,
friction?
so Fk into S.
That's it. Now Fk you can evaluate from the formula because we know Fk is mu into n. And what is n here, by the way? What is n here?
Mg cos theta.
We have to add minus mu into mg into cos theta into s. And now what is the meaning of negative work done by friction? What is the meaning of negative work done?
That the body is moving
That is the meaning of negative work. Were you
in the
present in the
opposite direction.
last lecture?
Yes, sir.
So what is the meaning of negative work?
When displacement is opposite to the force applied direction.
No, no. What is the meaning is it energy given to the system or taken away from the system?
Given.
So negative means energy given. So you just go back and today only you should revise the last lecture, listen to it carefully once again, and maybe listen to it maybe 2 to 3 times. So that's very important. So negative work done means the energy is being extracted from the block. So block is giving off energy to the friction or friction is taking energy away from the block. So it's energy taken away from the system. It's not given. And that is the meaning of negative. So coming back to the last force, which is gravitational force, mg. What is the work done by gravity? What we can calculate?
So is it Mg into S sine theta?
Correct. It is mg into s center is the right answer. Or you can say the component of gravity into s. So we have two way, and this is going to be positive or negative. This is going to be positive because the direction
Because
of
it's
force,
going down.
yeah, it's in the direction. So it's going down and force is also down. So in a way, the displacement is as per the nature of force, it's going down. And therefore it's mg sine theta, or I can say into s. And it's because it's positive, so this is the energy imparted to the block by the gravity. So now in 3/4 scenario, the normal is doing nothing in terms of energy. It's neither giving nor taking. Friction is taking away the energy and gravity is giving the energy. So the total energy received by the block is how much? The total, if you add
Adding
all,
everything.
what we get is mgs into sine theta minus mu cos. So the meaning of this is that this is the total energy received by the block. Now the question is how the block will manifest this energy. So we know that the only energy which a block or any mass reflect or manifest is called kinetic energy. So the initial kinetic energy of the block is 0. Then it receives some energy, and adding this energy will make a different value of kinetic energy. So we call K finite. So in our particular case, this was 0 because you started from rest. This is the energy which you received, which is mg s sine theta minus mu s cos theta. And this is must be the Ke final, that is half m, let's call V square in the final velocity. And if you solve this, we'll get a simple answer. V equals to 2gs sine theta minus, no, not 2s, it's 2 or simply let me write V under. So this is the velocity of the block when it will reach the bottom. So we can get the value, and because the plane shape we know, so we can also find the component also. So it will have direction like this. So velocity vector is this way. So now it will have two components, one horizontal, other down. So in case if you need component, you can also do so. Next, we can do some more problem. I think we did this in the last lecture as a demonstration. Let's do it again. So let's first do the ABD. So I may ask you a question like this, like find the velocity as a function of displacement x. If I say let's say m2 goes down by x, or maybe y is better symbolically. So if m2 goes down by x, then what is the total work done on a system m1 and m2? So find W total on m1 and m, and then you can find the work done total on system.
So the M2 is going down by Y.
Yes. So that is the information given to you. Let's say if the m2 goes down by y, then what is the work done by all forces on each block separately? So let's write the work done for m1 and m2 separate. So for m2, what we can write? How many forces are acting on m2?
So 2.
So what is the work done by each force? Like let's call gravity first. So what is the work done by gravity?
So M2GY.
Correct. So work done by gravity is m2g into y. Now what is the work done by tension force?
So 0.
Why? Zero as per which logic? How tension is acting
Upwards.
and how block is moving?
Downwards.
So what is the angle between the force and the displacement?
180.
So what is the formula?
Uh, Force into displacement into cos theta. So minus force into displacement.
So what we should write here? 0. Tell me what we should write here. 0 or something
Also
else?
minus ty.
Yes. So minus Ty is the ultimate tension. And now this is the total work done. So if the speed we can say V at after displacing Y. So this must reflect as a kinetic energy half m2 V square. Similarly, you can write it for F1, for M1. So for M1, what you can write? So because of the constraint relation, we know that if M2 will go down, then M1 will go up.
Up by t.
Up by.
Sorry, y.
So what we can write here, work energy theory, like the work done by net force, all force. So what is the work done by tension here?
Ty only, but plus ty.
Gravity,
Minus m1 gy.
and this must be equal to this is the energy received. This is the net energy received. So this must be the kinetic energy of the block. And
Yes.
because the constraint says that both will have same velocity, as we learned in the laws of motion, you can again write half m1 v square. So now what is the next step to solve this question? Adding the equation 1 and 2. So now m2 gy minus m1 gy. So we got the velocity as m2 minus m1 upon m2 plus m1 into 2 gy. Okay. So the v square we can also write as 2 gy into difference of mass upon sum of mass. And now if you differentiating both sides with time, now our answer is here done, but let's go one step further. Differentiating both sides with respect to time, we have what we have 2v dv by dt is 2g dy by dt. Rest are numbers, just write as such. This will cancel out, and v dy by dt we call acceleration, and dy by dt we call velocity. And what you get is the formula of acceleration. So anyway, that we did in the last lecture as well.
So can you show it again?
Yes.
The page. Yes, sir. Done.
Okay. So now we have to do some more questions, something like this one. So let's say we have two blocks of mass m and 2m. Now we are supposed to find the velocity of each block if the 2m mass will descend by height h. If it descends by height h, we are supposed to find the velocity. So now we cannot say that if 2m will have velocity v, then m will also have v. They will have a different velocity which we need to use using the constraint. So the important part here is to find the constant relation, that what to write v and this relation. Also the other part is the displacement relation. If the 2m goes down by h, what how much it will go? We can say it will go maybe h dash. Now the easiest way to find the constant is what? I hope you remember the laws of motion chapter. Tell me guys.
Sir, it will be 2h. No?
Sure. So what is the relationship between h dash and h?
Sir, h will be twice. No, h will be half of h dash.
Correct. So we can add the T and H relation. So 2T H dash, because that's the net tension into displacement, minus TH, because tension is upward going downward, must equals to 0. This is what we do for the constant relation. And this will give you H dash equals to. So now constant relations are very important in solving the question of work energy power. And therefore, if you differentiate dH dash by dt, this is also dH by dt. So in fact, the velocity of the first mass, if I call it V1, is actually V2 by 2. So again, we have similar relation for velocity. And now, knowing this formula, we can actually derive the V2 and V1 using the work energy. So let's add the work done by each force on each block. Like we need to also mention here M2G, 2mg, mg. Now, what you can avoid right now straight away is work done by tension, because what we realized in the last, question, that if you add both the equation, the Ty gets cancelled out. It means the tension will never do some net work. It will do some positive and some negative on the same part of the system. So the total work done by any internal constant force, that we call a constant force, will always add up to zero. So though there's no need to think of tension work when you consider all masses, and if you write the work done by each force. So don't write the work done by tension. Just write work done by other force than tension and add this one. Yes, you can write. You are free to write the way you have learned. So we can say that applying work energy theorem. So what we can say? Work done by gravity on system Now it turns out to be the gravity is the only force for the system. There is no other force actually. This must because you're changing kinetic energy. So let's write the work done by gravity on each block. So we'll begin with the 2m block, and on 2m block, what is the gravity work? So gravity is acting downward, and dispersion is also down. So we can say work done is 2m
2 mgh.
g. So 2m into gh actually. So 2mg into simply h. Uh, What is the work done by the gravity on the m block? So it is
The
acting down.
same.
It's going up.
It's
It
going
is
up.
same. So what is the work done by gravity here? Same.
No, it will be minus 2 mgh.
Minus. Why? Like you are only supposed to write the force and dispersion. Don't try to write anything else from your mind. Like if something random coming to your mind, just avoid it. So what is the work done by gravity on M block?
So it will be negative mgh dash.
Correct.
And h dash is 2h. No, h by 2. So
Okay.
mgh by 2.
Now when we write the kinetic energy, we write for the entire system. So we have block like half M V1 square, and we have block half 2M V2 square. Initial was zero. So this is the final energy. Initial is zero. So now we have to just substitute the value. So let me put it here. So now let's substitute the value. What you can write is 2mgh minus mgh by 2 equals to half m. So I will replace the v1 square as v2 square by 4 from this relation is half 2m into v2. So that's okay. That's what we are looking for. So now this will become 3mgh by 2, and this is equals to you can see here you can take half m common and become half m as such. And if you take half m common, what we get is v2 square by 4 plus 2 v2, which is equals to half m 9 v2 square by 4. So now we can just solve. Three three are 9 and 2 4 are 8. So v2 square will be 4 gh by 3. So v2 turns out to be 4 gh by 3 and 2, and therefore v1 is half of that, which is gh. Now these kind of questions are very common, and you need to have the kind of mastery over solving such questions. Okay.
So the minus 0 we did in the work energy theorem is because they had no initial kinetic energy.
Correct, 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 correct. In fact, what I will do is, if you have written this, then let me done.
Yeah, so done.
Let me just complete this working theorem concept. So, what is work energy theorem? So, it comes from the Newton second law. So, So we know that the net force, I mean the net external force is dp by dt. And for constant mass system, when mass is not being added or subtracted, when mass is a constant, and p we write as m into p. If m is constant, then dp by dt turns out to be m times dv by dt, which is not the case always, but this is what we can write. And therefore, we can also write f external equals to m dv by dt. Okay, so this is what we can write. Now let me write this in one dimension. If a block is moving in a one dimension, and if the force is F, so we write F equals to simply N. And therefore, uh, you can just write F, and A we can write as in an interesting way, we can write as V dV by ds, or you may say dx. So basically, F dx is equals to M V dV. I'm taking F as net force. If we just integrate the net force over the displacement, let's say 0 to x, then the velocity will change from u to v, and this is nothing but the work done. So we call the total work. And on the RHS, the m we can take it out, and v dv gives v square by 2. Putting the limit u to v will give you half, which is similar to writing delta. Because now we are concerned about the uh, energy part. We know that energy can only be changed when you change the magnitude, not the direction. So if a particle is moving and changing the velocity will not make sure that it will have some energy part. Energy is only meant for magnitude part. This is one of the derivation. The other derivation is by using vector concept, because we know that F external is m dv by dt. So to find the work done, we need to multiply or take the dot both sides with ds. ds. And now this F dot ds, and this we can write as dv dot ds by dt. So we are just doing the rearrangement, and F dot ds turns out to be m dv dot v, but because we can enumerate the dot product inside, we can write as d v dot v. And what is v dot v?
V square.
So I think I need to do something more here. It's dv dot v. So, yeah, that's good. But okay, yeah. So we need to also do one more thing, one small manipulation which I need to do. So basically, this will have some change here. Not this. We have tried v dot v by 2 actually. Why so? So if I differentiate v dot v, so what you get is you can take the first term outside. So v dot dv plus you will also get dv dot v, and it's the same thing. You can see it's the two times of v dot dv or dv dot, because it's a commutative law. And therefore, this term we can replace by dv dot v whole by 2. So that's why to replace this, I need to divide by 2. So eventually, if you integrate f dot ds, this will give you m by 2 into v dot v is v square, so d of v square. And integration of v square will, I mean, d of something is something only. So this will become again c. So you can derive from here also in vector form. You can derive, because we derive normally for one dimension. We say that it's true for all dimension. And otherwise, if you want to prove it for the all dimension at one time, then this is the way to go about it. So work mechanism simply says that for a given system of maybe one block or two block or maybe hundreds of
Sir,
blocks.
Anish, our previous question.
So for a given system, the total work will always change the kinetic energy. So the other way of thinking is the initial kinetic energy plus energy transferred as a work is equals to final kinetic energy. If the total work is positive, then total energy will increment, and if the total work is negative, then it will decrease, and if the total work is zero, then it will remain the same. So we have essentially three conditions: positive work, negative work, and no work, and that is how we can derive the condition. I hope this is done.
Yes.
So this is the work influence, nothing much. Okay. So let's do some very typical problem that we did in the chapter of laws of motion and friction, but that can be simplified easily using the energy concept. So imagine we have an inclined plane with a block at the top. So there was a block actually at the top, and it starts with rest, and half of the plane is smooth and half is rough. This is smooth surface, and half is rough patch, as you can see. And it turns out to be that while coming at the bottom, the block again comes to rest. So what is the value of mu? So the initial kinetic energy is given and final is given, and you can see from the energy part that there is no net energy given to the system. It means whatever was given, whatever was the positive work by some force, there was an equivalent negative work by some other force, and that's why the net is zero. So by applying the work energy theorem, you can directly get the relation of mu. What will it answer? So what we should write here? Tell me.
The total work done should be for the delta Q.
Yeah. So you just need to write the work energy sum. Just draw the ability, find the work done by each portion, add up to 0. That should give you the answer. So what is the answer? Tell me quickly. So what is the work done by gravity here?
mg sine alpha into L.
Mg
mg sine theta.
is work done.
mgl sin theta.
L multiplied by L.
Okay. So the displacement of the gravity is how much? Like how far it has moved. So I mean, coming from top to bottom.
12 sin theta.
So it is mg sin theta into 12, not L. Now what is the work done by friction?
minus L
Minus L is the answer.
into
So minus L into
L
g
into
mg cos theta.
yeah the frictional force.
Correct. So now what is the total work done? The sum of these two. So the total is simply sum. So you can say mg sin theta into 12 minus mu mgl cos theta. This must add up to 0. So therefore mgl will cancel out. So the mu turns out to be 2 times theta. That's the answer. Now if you recall back what you did to solve the same question, you will realize that it was really lengthy. So now this is the easier way. Now even if I change the L1, L1, L2, if I make it any ratio, you can still find the answer. The work energy theorem gives a very faster way to solve any question. Okay. So let's do somewhat challenging problem. Now this is definitely a challenging one. So we have a support, as you can see. No, this is a big support. Okay, so you can see that the length of the rope is given. The pulley is 2 meters away from the wall, and the block, the upper block is 1 meter away from the wall. We have two blocks. And now the system is released from rest. System is released from rest. You're not supposed to solve, but you're supposed to write the equation. So if you release from rest, what will happen? How the block M1 will move, assuming that M1 is much heavier than M2. That's the consideration. M1 is much heavier. Don't worry. Now, much bigger is not a good thing, but it's okay. So now, what will be the path of M2? How M2 will move further if we release the system from rest?
Sir, which one is greater? M1 or M2?
M1 is greater. If M2 is greater, then it will remain same, like somewhat it will dip and will stop. But the question is, M1 strikes the wall. It's given that M1 strikes the wall. You can say if M1 strikes the wall, then find the speed of M2 just before M1 hits the wall. That's the question. Okay. So what will be the path of M1 block? How exactly it will move? Any guess?
Towards the wall.
Towards on which path?
So slant
Uh,
path.
it will be a circular path of this radius. Because it is attached to a thread and thread cannot change the length, so it will fall on this path. So while M1 will trace the path, it will be coming somewhere here, keeping the length 1 meter always. So when it is about to hit, when it is about to hit, so when it is going to strike the wall, it will be somewhere here, and the direction of its velocity at that instant will be somewhere horizontal. So let's call it V1. Now, by the time the M1 will come here near the wall, the M2 will take a new shape because the thread is here. So the blue thread will elongate, right? So now this thread will be somewhere here because it is attached to the block. And the block will be somewhere here, pulled upwards. And it will have some velocity. Let's call it a V. And now the green one which you saw earlier is now hanging below. Now you can ignore this tilt, but because we consider the size of the block as almost zero. So these all are meant for the illustration purpose. Really make it small. Another question is, what is the work energy theorem in this particular case? What is the working by gravity for each block? So we need to find this displacement first. What is this one? Now what we know, the displacement of the A1 block is exactly 1 meter because it has come down by 1 meter. So what is the value of this y? Can you find the y value? So it turns out to be yes, we can find y value. How we can find? Because if you use the Pythagoras, I mean, for the above triangle, this triangle, you can see that this is 2 meters, this is 1 meter, this must be root 5 meter. So from 1 meter, it has stretched to root 5 meter here. So the block must have moved how much? So here y becomes root 5 minus 1 meter. I hope you can understand this. Right. So the new length on the of the blue rope on the left side, I mean left of the pool, you can see is root 5 meter. Earlier it was 1 meter. So it must have pulled the block up by this value, isn't it? And now we can add the work length. So what is the okay? No, before that, let me add the constant resistance. But that's very important here. Constant. So what is the relationship between V1 and V2? You know it. So let's call this angle theta. This will be also theta. So why? What we know that along the rope, the component of velocity remains same. So V2 must be equal to V1 cos theta. What is cos theta? Cos theta is based upon hypotenuse, which is 2 by root 5. Everything is known to us. So V2 we got V1 we got the constant resistance. Now the next part is only writing the work energy theorem.
Yeah, and show the progress.
Yeah. Okay. So now if you apply the work in theorem, you can definitely write work done by gravity, and there is no actually external force except gravity. So only gravity is the only one. So we just need to write delta. But we are writing for system, not for individual, for both blocks. So for M1 block, we can directly write M1 G1 because that's the displacement. But for M2, it is minus M2G root 5 minus 1. And this must equal to half M1 V1 square plus half M2 V2 square. So maybe if I give, but that will maybe not answer. So what we are getting is M1 minus root 5 M2 plus into G equals to half M1. And V1 square is okay. What is okay? V2 is V1 plus it. So let's write V1 square. Uh, let's substitute V2 because that is V1 plus it. M1 plus M2 minus root 5 M2 into G, and this gives us M1 plus M2. So everything is known to us. We can, if you want, we can substitute. and given the marks, you can get the answer. And this will also give you the condition for hitting the wall. So what will be the condition for hitting the wall? Can you guess? The term in the root must be positive because the square root of only positive numbers we can calculate on a real world. So you can also derive the condition for hitting the wall. And that is m1 plus m2 minus root 5 m2 is positive. So you can say m1 is more than, maybe the ratio is a better thing to define. And this is roughly 1.2. Any value which is more than 1.23, you can choose as a ratio and then you can solve the question. It will hit the wall. Okay, so this was the JE old problem, like from the 90s, and it was 10 marks problem. So definitely a nice problem to understand and learn the various concept of application of working theorem and the constant relation. Okay,
So
so
can
now
you show
you
the displacement would come? Understood, sir.
no. So far I have
Sir,
been
I want to
using
note the condition for hitting the wall.
make the square root positive. That's it.
Sir,
I
done.
hope you. So now I'm using continuously a word constraint. So we really need to elaborate the term constraint. What do we mean by constraint? So now we'll discuss the something called. So we're talking about the internal constraint force. So the word constraint means which restricts your motion in some way. For example, the floor or the ground on which you walk never let you go, or dent or go inside the floor. So when you walk, you don't go inside, you go only forward or backward. So what is stopping you to go inside? What prevents you going from inside? I mean, You
Normal.
don't, it's normal, exactly. So the role of normal is to constrain your motion. So it act as a constraint force. So the normal is called internal constraint force if it prevents the motion of one body to move in certain way only. So you cannot move normal to the, or you cannot move along the normal direction relatively. You have to move together. You can't move relatively. The idea is normal is a constant force. So we say normal reaction. Now, what is the other constant force that we are very much aware of?
Friction.
Which friction? Static or kinetic or both?
um,
Which friction? So which prevents the relative motion? Pardon? Pardon? It is a static friction.
So is this diagram going to be big or small?
Pardon?
The flow chart you're making, is it going to be big or small?
Small, very small. This is the only filter. So the normal reaction and static friction are the basically constant flux because it offers you a constrained motion, not a free motion. So when we say there is a static friction between two surfaces, it means one cannot slip over the other. That's constraint actually. And the last one, not to forget, is tension force. Because again, we say if bodies are connected by a rope or a string, and the string is always taut, so keeping the string always taut puts a constraint on the motion of the connected parts. So if I say that all connected parts must move in certain way, it means all connected parts are constrained to move in certain way because they are supposed to keep the string taut all the time. So keeping the tension in the string all the time without making it loose is a constant relation. So it gives you constant to move. That's why we also have a constant relation in tension that we learn in laws of motion. So these three forces, tension, normal reaction, and static friction, not the kinetic, because in kinetic friction we do have a relative motion. So this is not a constraint. So now, what is the essential fact about this constant force? Basically, internal constant force. The answer is on a system it never works. So on a system, if you calculate the work done, it will always give you zero answer. That's the fact. This is what we need to remember. The total work done by internal constant force on a system is always zero. The total work done by internal constant force on a system is always zero. That is internal constant force can do positive or negative work on parts of system, but total is always zero. that is their job is to redistribute the energy within the system. Redistribute energy
So what have you written total?
within the system. Pardon?
So what have you written after total?
After
Total, last line.
the total work done, the
So
total work
last line.
done by internal constraint force, constraint. I need to improve my handwriting. So the total work done by internal constraint force on a system is always zero, and that is the internal constraint force can do positive or negative work on parts of system, but total is always zero. So sum of work done by tension force for the entire system, if you take care of every part of system, it will always sum up to zero. So that's why while writing the work energy theorem, we should not write the work done by internal constant force. You can just avoid and write the rest. Now, if you want to write, then you have to write for each system separately, and then you will see that all will add up to zero. That I have demonstrated in the beginning. So, as an example to remember this three cases of, three internal constant force, you can just take three examples.
So once again, can you show the previous? I just have to note one line.
Just
So done.
oh. So imagine we have an elevator and we have multiple blocks kept inside the elevator. So we have block one, and there's a block kept over this. So now my system is these two blocks. So M1 plus M2 is system. So now, of course, if you draw the normal action, there are two normal acting. One is acting between the floor of elevator and the M2 block, another is acting between M1 and M2. So we are only interested in the internal normal, not the normal applied by the floor, because that's not internal, that's external. So if you draw the ABD of each individual block, and we'll only draw the normal section. So one normal will act like this. N will act on the block like this. If the elevator goes up with Y value, so then the work done by normal on M1 is how much? You can see clearly that work done by normal on M1 block is definitely Ny, but the work done by normal on M2 is how much? Minus Ny. And therefore work done by normal on system is how much? Zero. So that's a simple proof that internal force because comes in pair and they have equal in opposite direction. So the other way of proving is that because for any system, two, let's say we have two block system or two mass system, and it's not about just constant. If the internal force are constant force, So they will have similar displacement. That's interesting about constant force. If the internal force are not constant, then they will have different displacement. So that's why, because we know that F12 dot ds plus F21 dot ds, I'm writing work done by each force, is same as writing F12 plus F21 dot ds. Because the constant force having the property that they will always suffer similar displacement. So ds cannot be different. And from Newton's third law, we know that the sum of the internal force is always zero. So this turns out to be 0 dot ds, which is simply 0. So it's a null vector. Null vector dot anything is 0 only. So this is simple proof that why internal constant force does 0 work. Now, if ds values are different, if we have ds1 and ds2 for each force, then you cannot add up to 0. That's not, I mean, there is nothing called necessary condition. Now, it may or may not be. I mean, we have no idea about, it will not actually. In fact, no. Because these are equal in magnitude, so definitely there is no question of 0 work. So if a force is not constant, then ds will not be same. That's the meaning actually. So if internal, I mean, that's like a note, you should also take a note of this fact also. If internal force is not a constant force, then we can add F12 dot ds1 plus F21 dot ds. I'm just writing the element 2. And we know that F12 is minus F1, so I can rewrite this as F12 dot ds1 minus F12, because we can replace this by minus dot ds2. And what I'm trying to demonstrate that I can take the force and then I can take ds1 minus ds2. So the work done by internal force, which is not a constant force, turns out to be something very interesting. And we write as a F12 dot ds relative. I mean, 1 2 means 1 minus 2. So now ds1, ds2 is the individual displacement, but it turns out to be the relative displacement. So if the internal force is not a constant force, then what matter is the relative displacement multiplied by the F12. This is the work done. So this is very, very important concept actually in working physics. This is something which should be taken care of, else you may commit various conceptual mistakes. So the internal constant force, now you need to understand the concept. The internal constant force means that the point of application will displace equally for both the pair of forces. And if the internal force is not a constant force, then they will have a different displacement. And so the work only depends on the relative displacement. The individual displacement does not matter. So we'll talk about this very soon. I mean, let me finish this part first. Now, these are some advanced concepts which you need to apply in tough problems, which you will see very soon.
Sir, can you show last page?
And this is the work done on a system. Actually, this is system. So what we are finding is for the entire system, not for individual. So work done by
Sir, done.
internal force, if not constant, will be not be zero. If constant, it will be zero. Okay. Okay. So look at this. I mean, the second example. So for tension, we have seen already it's a zero. I have given you the example of Atwood machine in which the tension work is plus T1 minus Ty, so it is again zero. So let me give you the other example, like and static friction is again the same. I mean, if it is a static friction, let me anyway draw this just for the sake of completeness. So let's say we have a plank and having mass something. And above the plank we have another block of mass m1. So now we have a, you can see, and maybe some force is applied here to push the lower block, but because of the friction force present between the block, it also moves together. So now after traveling some distance, it is here, but it is also here. So you can see that because there is a static friction, so there is no question of a relative motion. So displacement of each block will be same, no matter what. But if you draw the FBD of M1 block, so I can do it. So if you do the FBD of the, I mean, both the blocks, the M1 will experience friction force forward because in the very beginning M1 is not experiencing any force, and the capital F is trying to push M2 forward. So the direction of friction will be forward on M1 because okay. And on M2 it will be backward, but this will be Fs. So if I call this displacement as S, then definitely we can say work done by friction, static friction on M1 is plus Fs into S because that's positive. But the work done by Fs on M2 is definitely negative, and the work done by Fs on system is definitely. Now these are some concrete examples that you can keep in mind just to recollect the theory, and this simple example will be, I mean, should be retained by the brain. So the idea is you need to keep one example so that you can answer the conceptual question. Okay. So work done by internal constant force on a system is zero, but it does not mean it is zero for each part of system. So static friction can do some positive work, can do some negative work, but as a whole, it does zero work on a system. And now what we're talking about is the internal constant force, not some other friction. Now, what if the internal force is not a constant force? So that's a very famous example called work done by kinetic friction on a system. Now, this we need to take care, particularly. The reason is variety of problems are based on this. Not here, maybe in the next chapter called center mass, and where the notion of work done by kinetic friction is very important, like how to calculate. So let me learn. I mean, let me teach you this as a separate topic. This will help you in recalling it easy. So the heading is work done by internal. Now this is important. This is what I want to emphasize. So work done by internal kinetic friction on a system artifact. So let's take some concrete examples, maybe which you can relate to. So we have two planks. So you can see the first plank. Let's call it, and it is kept on a smooth surface, so there is no friction. So even a slightest push will make it move. That's the idea. So what we do next is we take a block and we throw it over the M1, M2 block. So now M1 is thrown over M2 with some velocity, initial velocity, let's say V0. And there is a friction coefficient between the block and the plank, you can say that. So plank M2 and block M1 will have some frictional forces, so they will rub each other because M1 is trying to go forward, so friction on M1 will act backward. So maybe after some time, if you plot M2 is here, but now the block will not be at the same corner. So before the block will rub and will come to rest, so what I'm assuming, the block might rest somewhere here, and because of the friction, you can think that M1 will decelerate, M2 will accelerate, the velocity of M1 will decrease, M2 will increase. So the situation when the relative motion will stop is called when both will have same velocity. Both will have same velocity v and v, which will be different from v naught definitely. Now, how to find v and v we will learn in the next chapter called conservation of momentum. So if you conserve the momentum, you can also find v value. But that's a question of different topics. So right now we are only considering the work part. So now what we can see clearly that displacements are different. I mean, if I say that this one has displaced by this value, so now there is an additional displacement of M1 block. So the additional we call it relative x relative. So now from the ABD of the force, we know that friction on the block will act backward, and the friction on the plank will act forward. But now this is Fk. So now, what is the work done by kinetic friction on M1? It turns out to be minus Fk x plus x relative. What is the working by kinetic friction on M2? It is only Fk into x plus taking forward. So what is the work done by kinetic friction on system? Uh, System. Just write system. So the system it turns out to be minus Fk into x relative. Now this is what I am trying to write in the vector notation in the previous page. This is saying that it is this sorry, the friction force and the, so I'm taking F12. force on 1 due to 2. And now what is important here is that the network is negative. Now this negative is very important. And what it says that the total work done by kinetic friction on a system cannot be a positive number. It must be a negative number, which means kinetic friction as a whole always dissipates the energy of system. As a whole, it always reduces it. It will increase energy of one part by some value, as you can see Fkx below, but the decrement will be much more than the increment part. So it will decrease more than what it will increase. So the net it is going to decrease. So imagine that if you give a glass full of water to a small kid and tell him, I mean him or her to carry it from one room to another room, there is a very high chance that she or he will spill or splash the water on the floor while taking it from one place to the place. The child is like kinetic friction, and the water which is, I mean, splashed out or spilled out of the glass is kind of lost in energy. So now she is doing some positive work, but in a way she is losing some part of the energy, and that is exactly what the kinetic friction does. It does some positive work, but it at the same time it does some negative work, and negative always dominates over the positive. The net result is always the loss of energy for the system as a whole. So M1 and M2, if you take as a system, at the end of this work, it will lose some energy. Now, what is most, I mean, more fascinating about this is that it only depends on how much they move relatively. The absolute motion has no relevance here, and that is the crux point. This is the crux. The absolute motion should not be taken care of. What should be taken care of is the relative motion, and that is why this question becomes the most challenging problem in the next chapter called conservation of momentum. So there with momentum, conserve momentum, you can actually find the x relative, and there are various methodologies. So now this is the important part. Work done by kinetic friction. So now what I can say about this entire thing is in one line. So what is the initial energy? You can look at the energy. The energy is how much?
0.
No. What is the energy of system initially? The kinetic energy.
Okay, हाँ half है V0 square. Half M1 V0 square.
Correct. Correct. So now out of this energy, how much you lost? So what is Ke final? So I can say the initial plus work done by all forces. But here it turns out to be negative. It is Fk into x relative. And this is the kinetic energy, the final energy. Now, the conservation of momentum actually gives us the velocity part, the v part, and therefore we can find this value easily. We know this value easily, and using this value actually we calculate this value x relative. So that will be the question of the next chapter. I mean, this is just one small line of conservation of momentum part, which is pretty easy. But just because I haven't taught you, I'm not emphasizing here. So the idea is, unless we do not understand the energy loss or gain, it's impossible to solve the question. So the initial energy was half m1 v naught squared for the system as a whole, and the friction has wasted or dissipated this energy. And the left energy, the leftover energy, is the difference of the two. Okay, so basically this is your half m1 plus m2 into v squared. Now, if you know x relative, you can find the v and vice versa. So if you know v, you can find x relative. Okay. So this is the way of solving the question. And this is very, very crucial question. Actually, we need to have the mastery over this particular question.
So can you show
So
the
now
previous page?
we have seen all the work done by internal force, and I put the internal force into two categories. One is the internal constant and internal non-constant as well, we can say. So because we have just only one force which is non-constant, we have one more force that we'll talk about later on called spring force, which could be internal and non-constant because spring can be moved. So we are never sure that if two blocks are attached with a spring, then they must move equally. That's not required. So they can move differently. So if a spring force will bring into picture, then something interesting will happen. So we'll see that.
Well done.
Now, so now internal constant force, if we have an internal friction force, if it is a kinetic friction, what we must understand that it is going to dissipate the energy and therefore the dissipation will become a heat developed. So there is something called heat also. So in the chapter of calorimetry, you may come across something like that. So question is in case of work done by internal kinetic friction. So in case of work done by internal kinetic friction, the delta H called the heat produced or heat energy. Heat itself is the heat energy is equals to work done. I mean Fk, the kinetic friction into x relative, and we write a positive value there. We don't write negative. Negative means it is wasting or dissipating the energy. It is reducing the energy from the system. So it is producing heat. So this is the value wise it's positive. You can say you can take more. So if the work done by kinetic friction is negative, it means all of that loss is converted into heat energy. And now if I choose this energy, heat energy to melt a lead ball, I can say ms delta theta, and we can solve for uh, change of temperature of some other object. So again, this work we can relate with some other situation in other chapter, and that's why this question is again one interesting one problem where we need to think something like that. Okay, so we have seen one particular variety of question, but is this enough? The answer is definitely no. Okay, so in case of work done by internal kinetic friction, the heat produced is this much. So now in the previous case, first they will rub each other, they slip, and after some time they will move together. And the moment the velocity becomes equal, the friction will vanish. I mean, because there is no relative tendency. So, I mean, what I can do is I can just do at the instant both the blocks. Now, for friction to act, the relative tendency of motion is necessary. So when the block will move together with the same velocity, then there is no question of friction because they have lost the tendency of relative motion. Okay. So that's very important. So now let's move towards the
So what is
very
the instant at which interval?
pardon.
Sir, at which instant?
At the instant when both the velocity of the velocity of both the blocks becomes same. Now, what you can realize that initially velocity of the so if you plot the graph of v versus t, and because the friction will produce the constant acceleration, so the first block m1 will will have some velocity, let's call v naught, and it will decrease. On the other hand, m1 m2 will have zero velocity and it will increase. So at one particular time, well, let's t naught, the velocity of m1 will decrease, m2 will increase to the same value, and that's called v. And after that, it will move with the same v forever if the ground is frictionless and things are maintained. Understood? Is that clear? Is clear? So this is the again the heat calculation. So they'll ask you find the heat produced in the process. So the heat produced in the process is always uh, the work done by kinetic friction. So constant force cannot produce heat because they don't work any, they don't dissipate or do something. So only the internal kinetic friction is able to produce the heat, no other force. So that's why this again this answer is very important in a way that it can be employed in variety of questions and situations. So try to remember. Okay. So now we'll come back to the work done by. Okay, so far if you see carefully, so far whatever we discussed was work done by constant force. So all the force maintain their direction and magnitude, and we just wrote the values. So now what if the forces are not constant? They change their direction and they change their magnitude and so on. So the next concept is called work done by a variable force. So I think I gave the derivation earlier. Yeah, this one. So now this is the basic thing. The work done by variable force we can write as F dot ds. And let me elaborate here only. So for two dimension or three dimension, the F you can further write as the component x component I cap, y component j cap, and the z component k cap. And in fact, ds you can also write as dx I cap and dy j cap and dz k cap. So the F dot ds turns out to be fx dx plus fy dy plus fz dz. So you can divide into three parts. Okay. So once you know the fx, fy, and fz value in terms of x, y, and z respectively, you can integrate. Okay. So now this is the basic formula which we need to remember. So what is the rule to remember that whenever the force is variable, we cannot think about work done over a big displacement. Rather, we need to go back to elementary displacement and then check what it does. and we have to make sure that for every elementary displacement, we can calculate the work done by knowing the force and direction and everything else. And from there, we can derive the network by integrating over all such small displacement. So the takeaway from the discussion is for work done by variable force, we can only write elementary work first. And once you write, you can go further, integrate and get the answer. So don't think of writing Fs cos theta, write F dot ds, or write F cos theta into ds, or write F into ds cos theta. So whatever you do, make sure that you do it for the elementary displacement. So you're not supposed to do it for the big displacement. Okay. So having said this, let's go back. So work done by variable force. So just for one second illustration, the dw is something which we need to be bothered about, not the w. And once we know the dw value, we can integrate further and get the answer. So the very famous question is called the Hill problem, which perfectly sums up the problem, like this concept particularly. So what is this Hill problem? So we have a mountain, a hill of a random path. So no, path is not important. It could be any shape. But eventually the height which will reach is given to you. And now this kind of calculation is maybe pretty for the first time. So this is something we'll learn. So let's say you go from bottom to the top, and this is h, and the length is h. So now, what is the question actually? Question is says that a block is pulled along the surface of the hill slowly by some external agent. What's the question? A block is taken from, let's name it A to B. From A to B by applying external tangential force slowly. I think slowly should come here. Okay. Now the coefficient friction between the block and the surface of the hill is given as mu. So while the block is trying to move, the friction is always acting. Of course, normal is acting, gravity is acting. But the only thing is, it is taken away slowly. Slowly means, now that's very important. What is slowly?
No acceleration.
No acceleration, correct. So the idea is the net tangential force is always zero. So the thing which we need to realize that slowly means no acceleration, which means net force, no, summation of all force is zero. So this is the
The
concept.
summation ft, no?
Summation of
ft.
F.
So
No,
force
in
and
fact,
tangential.
no, it's not only tangential. It means in all direction. In fact, so it is F0, and of course, if F is zero, then Ft is zero and Fn is zero also. So whatever direction you want to take, you can take, and every direction will give you zero answer. Okay. Yeah, of course. I mean, FP is zero for sure, because if force vector is zero, it means all components are zero. So another question is, can you find the work done? Do you want to try this? No.
Yes.
Okay, so I'll look at answer. So now how to go about this problem? So what we do is,
We take the displacement of the block.
no. So you want to try this question?
Yes.
Okay, go ahead. I'm giving you 2 to 3, 4 minutes. Maybe you can think about it. Okay, so I think I should solve. So what we'll do is we'll assume the some instantaneous position of the block, and it looks like the block is actually lying on some inclined plane, and the plane is making some angle like this. At any instant, this is the block position. Let's call this an theta. And now you can ignore the hill and think about this plane for that moment, because for the next ds displacement, nothing will change. Normal, gravity, and of course friction, because it's trying to go up, so friction will act backward along the plane direction. So this is the kinetic friction, this is the gravity, normal, and of course the tangential force which is moving it. So we are supposed to find the work done by the agent in doing so. So how much work agent will do to take it from A to B? To find work done by, because we need to mention work done by whom? By external agent. So now it will be displaced by ds. So we can say work done by agent, elementary work. Now, as I said, for variable first, we can only define the elementary work. So we can add this as f tangential ds, right? So we call it ds. So if you're comfortable so far, then we can move forward. Now ft is not known to us because the only information given is that it moves slowly. So now slowly will give you the answer for ft.
So please show the previous page. So that is the work done. What is written dw below dw?
Agent. It's
So done.
agent. Just remove this one. This is not equal. So this is the working by agent. Now ft what we can add. So to get ft we have to use this condition slowly, and that will tell you that ft is nothing but the fk plus mg sin theta. So we can add as so for finding the ft, use fvd, and from fvd what we can write is that ft is nothing but the mg sin theta plus mu mg cos theta. And theta is of course variable, we know that, but for elementary displacement nothing will change. So we can say dw is equals to ft ds, which is equals to mg sin theta ds plus mu mg cos theta. So here comes the interesting part. We cannot integrate such things like that because theta is not known. ds is, of course, we can do, but theta and s there is no relation, and theta is a variable, so it's not even constant. We can take it. But it turns out to be something very interesting that if this is the ds, if I zoom the shape and if I call ds, and if the angle is theta, so this is nothing but dy, this is dx. And the dy is nothing but the ds sin theta, and dx nothing but the ds cos theta. So what we never realized that this could be simplified as mg ds sin theta plus mu mg ds cos theta. And it turns out to be eventually mg dy plus mu mg dx. And now you must have realized that why I gave you the height h and the length l. So for a slow case, like when you pull it slowly, it turns out to be that the net work done depends only on the horizontal and vertical displacement. It has nothing to do with the shape of the hill. And so now we are good to go with the final derivation. Just integrate, and mg is constant. We have to just integrate dy, and mu mg is again constant. We just need to integrate dx. The y goes from 0 to h and x goes from 0 to h. And the overall answer turns out to be mgh plus mu mgl. So the first term is the work done against the gravity, and the second work is the energy lost by the friction. So in fact, if someone asks you what is the, this is the answer. No, this is the answer. So in case if I want to know what is the work done by kinetic friction for the entire journey, so it must be minus fk ds integration. I'm just writing all things together, and this was mu mg cos theta ds, and this is always minus mu mg ds cos theta, and this is mu mg dx, and that's what the answer is. Now this gives you another example that work done by kinetic friction. Work done by kinetic friction is something which only depends on the horizontal displacement, not the vertical. But the rule is that the normal must be mg cos theta. If normal is different from mg cos theta, we cannot apply it. And now you can realize that why it was written in the question that assume it's moving slowly, because slowly refers to the fact that v is almost zero, velocity is almost zero. So there is no centripetal force, I mean, developing. So normal is not different from mg cos theta. Because the path is curvilinear, so it is obvious to have centripetal acceleration v square by r. But to avoid that centripetal acceleration, the v was made zero, and so v square bar vanished, and therefore the only possible acceleration was tangential. But even that is because it's non-accelerating, so even tangential is also zero. So now this is something which you need to remember, that work done by kinetic friction for slow motion, like when you move something very slowly, is always equals to minus mu mg into horizontal displacement. Now this is again very important for me. This is like something you just need to remember. It's not something which you can just write and be happy about it. So these are some of the important derivation that we should remember the result itself to solve the good question or tough question with ease. So keep in mind, and gravity work is anyway does not depend on uh, this, I mean, path and all. So we know gravity work is always simple. It's only uh, vertical displacement, because gravity is constant force in this particular case. So if you remember this, we can solve some very interesting I mean, problems which are quite close to this. So let's take one example. It's a very famous one. So we have a semi-circular cylinder actually. So what we call it, uh, semi-circular cylinder. And now we have a small ball touching the center. and something interesting is there after that. So hmm. Okay, now this is the problem. So now we have a ball which is attached to a thread. A thread is passing over a semi-circular cylinder. And the coefficient of friction between the ball and the cylinder is mu given. So now again the question is, what is the minimum work done? Like we have to move the block, means this ball from there to there. So what is the minimum work done by F to pull the block from bottom to the top? So find the minimum work done by F. I mean F means basically agent, I'm saying, called agent F, in pulling the mass M from bottom to top of cylinder. So tell me the answer. It's pretty obvious. We have done this. It's the same hill problem. Pardon? Pardon? It's the mgr because h is r only plus mu mg r. Mgr 1 plus mu. So we may ask a question like this. So we have a random mountain. Again, a ball is taken from A to B slowly by a tangential force. F is always tangential. Now, in the above case, it is tangential force because the tension is always acting like this. So this is always tangential. And because you are moving it slowly, so tension is always equals to the gravitational component at different point of motion. So now a mass m is taken from A to B, and F is always tangential, and mass is moved slowly, which means you can always write n equals to mg cos theta as per the ABD. So what is the work done by F? Coefficient of friction is mu and the AB length is L, and this height is the maximum height is H1. Seriously, I mean, I don't know which one you will pick to answer this question. Okay, so L is the gap between A to B. So work done by F from, I mean, taking this A to B. Now these are very challenging problems. Like these were problems of Olympiad actually. The first stage, not a high stage. So quite relevant to JE questions, and these are pretty easy questions in a way because the concept is already taught to you. So now it's not difficult. Just tell me the answer. So what you need to remember is that the work done by the force is always the sum of the, I mean, the opposite of the work done by gravity and uh, friction. So it's the work done against the gravity and friction. So what is the work done by gravity here while going from A to B? So when you go from A to B, what is the work done by gravity?
Sir, mg h1.
So when you go from A to B, what is the work done by gravity? So when you go from A to B, what is the work done by gravity? Zero is the right answer. So okay, so it is a
Sir, ये
gravity
zero.
is zero. So work done by gravity is zero. So the first term zero. The only frictional work will come into this particular case because we have only a horizontal displacement, not the vertical one. So this is m. That's the only answer. Okay. Now imagine this was the question of Olympiad and online answer, but because this is the derivation behind this, so yeah. So now we have a really nice collection of problem from the variable force category, and I'll just give you one homework which you can try from very basic and solve this question. So this is the question. So now we have a really small block, and there is the frictionless. So at some instant it will be here, and it is attached to a thread. Um, Maybe I can kind of pulley a nice this one. This block is pulled by a force like this. So force is always pulling it, and the thread is like this always. So pulley is attached there, and, and uh, the magnitude of force that's a constant. Let's say F is constant. Okay, fine. No, no, no. F is constant. Slowly. Okay, so now the block is pulled from A to B slowly by the force F. Uh, yeah, F is constant. Yeah, you can take F is constant. So F is given. This is given. So block is moved from A to B by a constant force F as shown in figure. So maybe some other forces are acting, but that we're not bothered about. So the question is, in taking it from A to B, what is the work done? So we find the working done. That's the question. Uh, some interesting formula-based question we can also do. So the next lecture will be even more interesting. We'll see some of the nice mathematical pattern in the derivation of Unit. Then you can practice from SC Brahma and from the sheet which I have shared, and we'll discuss more in the next lecture. Okay, guys. I'm ending the lecture.